HighBridge, a division of Recorded Books, presents The Little Book of Black Holes, Science Essentials, by Stephen S. Gubser and Frans Pretorius. Read by Andrew Eiden. Preface. It was September 14th, 2015, almost exactly 100 years after Albert Einstein formulated the general theory of relativity. Two massive detectors, one in Louisiana and one in Washington, were undergoing final preparations for a science run aimed at detecting gravitational waves. Suddenly, and unexpectedly, the detector's instrumentation recorded a peculiar chirp. If we made this chirp audible, it would sound like a faint, low-pitched thump. 5 months later, after careful scrutiny of the data recorded by these detectors, the Laser Interferometer Gravitational Wave Observatory, LIGO, publicly announced their results. That chirp was exactly the sort of signal they had hoped to detect. It was the distant echo of a pair of black holes caught in the act of merging into a single, larger black hole. The physics community was electrified. It was as if we had lived for all our lives blind to the color red, and at the moment the veil was lifted, we saw a rose for the first time. And what a rose it was! Best estimates from LIGO indicated that the faint thump they recorded was the result of the coalescence, more than 1 billion years ago, of two black holes, each of them roughly 30 times the mass of the Sun. During the collision, some 3 solar masses worth of energy from the black holes was vaporized into gravitational radiation. Black holes and gravitational waves are both consequences of Einstein's general theory of relativity. General relativity predicts what sort of gravitational waves the LIGO detector should see in the event of a black hole collision, and the chirp recorded on September 14th was beautifully close to expectations. Not only is it a vindication of long-cherished theoretical ideas, this first detection event also augurs a new era of gravitational wave astronomy. The LIGO detectors saw one event of the sort we've dreamed of for decades. Now we want to explore a whole new garden of gravitational surprises. Science seldom involves mathematical certainties, so we should ask, how sure are we that LIGO construed correctly that the little chirp is the distant echo of a billion-year-old black hole merger? Briefly, the answer is, pretty sure. Everything seems to fit. The signal was seen by both detectors. Nothing else seemed to be happening nearby that would explain the signal. The signal was strong enough to see with the current device, but too weak to be observed by earlier technology. The hypothesis of a black hole merger 1 billion years ago doesn't conflict with our general understanding of astrophysics and cosmology. The key point is that we have good hopes of seeing more such events. Indeed, LIGO announced a second confirmed event that occurred on Christmas Day 2015, and a third that occurred on January 4th, 2017. These events are broadly comparable to the first discovery, and should give us significantly more confidence that LIGO is truly observing black hole mergers. Altogether, we believe that we are standing at the dawn of a new age in observational astrophysics, one in which black holes will play a pivotal role. In this book, we describe black holes, both as astrophysical objects whose existence is now almost beyond doubt, and as theoretical laboratories which allow us to hone our understanding not just of gravity, but also of quantum mechanics and thermal physics. Explanations of special relativity and general relativity set the stage in chapters 1 and 2. Then, in subsequent chapters, we go on to discuss Schwarzschild black holes, rotating black holes, collisions of black holes, gravitational radiation, Hawking radiation, and information loss. So just what is a black hole? Essentially, it is a region of space-time toward which matter is drawn and from which escape is impossible. Let's focus the discussion on the simplest black holes, known as Schwarzschild black holes, in honor of their discoverer Carl Schwarzschild. There's an old saying, what goes up must come down. Inside a Schwarzschild black hole, a stronger statement is true. Nothing can go up, only down. But we're not sure where down eventually leads. The most straightforward hypothesis, given the mathematics behind Schwarzschild black holes, is that a terrible, infinitely compressed kernel of matter lurks at its core. Colliding with that core is the end of everything. It is even the end of time. This hypothesis is hard to test because no observer who goes into a black hole can ever report back on what he sees. Before we go on to explore Schwarzschild black holes in more depth, let's first take a step back and consider gravity in some of its milder forms. From the surface of the Earth, if we impart a sufficiently large upward velocity to an object, then it will keep moving upward forever. The minimal velocity for which this is true is the escape velocity. Neglecting air friction, escape velocity is approximately 11.2 kilometers per second. By way of comparison, it's hard for a human to throw a ball faster than about 45 meters per second, less than 0.5% of escape velocity. The muzzle velocity of a high-powered rifle is roughly 1.2 kilometers per second, so slightly more than 10% of escape velocity. What we usually mean then by what comes up must come down is that Earth's gravity is strong compared with how forcefully we can propel objects upward using ordinary means. Rocketry is the modern means to conquer Earth's gravity altogether and send objects into space. To escape Earth's gravity, it is not strictly necessary for a rocket to go faster than 11.2 kilometers per second, though some rockets do. What can happen instead is that a rocket travels at a slower velocity, but has enough fuel to keep thrusting upward until it reaches altitudes where Earth's gravitational field is significantly weaker. The escape velocity from such altitudes is correspondingly smaller. In other words, a rocket designed to take a space probe entirely out of Earth's gravitational field must be going faster than the escape velocity at the point where the rocket stops firing. Now, we could ask, what if the Earth were much denser? Escape velocity from the surface would be larger because the gravitational field would be more intense. The densest stable form of ordinary matter in the known universe occurs in neutron stars. They pack approximately 1.5 times the mass of the Sun into a sphere of only 12 kilometers in radius, though this radius is not very precisely measured. Ordinary matter is completely crushed into the surface by the tremendous gravitational forces, which are something like 100 billion times stronger than the gravitational field of the Earth. Assuming a 12-kilometer radius, the escape velocity is approximately 60% the speed of light. But why stop there? As a thought experiment, we could imagine compressing neutron stars even further. If we compress a neutron star to a radius of about 4.5 kilometers, then its escape velocity reaches the speed of light. If we go past that point, gravity changes character completely. It's no longer possible for any form of matter to hold itself up against the pull of gravity. To move forward in time means to move inward in radius. Escape is impossible. This is a black hole. The central aim of the first few chapters of this book is to make the idea of a black hole more precise. A key concept that we'll explore is the idea of an event horizon, which is the surface of a black hole. It is a surface in the geometrical sense of being a two-dimensional locus in three-dimensional space. For example, in the simplest example of a Schwarzschild black hole, the horizon is a perfect sphere whose radius is called the Schwarzschild radius. The odd thing about a black hole horizon is that, at least according to conventional understanding, it is not the surface of anything in particular. At the moment you fall through it, you don't notice anything special. The only problem comes if you try to turn around and get back out. No matter how hard you try, using a rocket, a laser cannon, or any other means, and no matter what help you might have from outside, it is impossible to get back outside the horizon, or even to send an SOS signal out to say you're trapped. Poetically, we might think of a black hole horizon as the lip of a waterfall. beyond which space-time cascades ineluctably downward into a singularity that destroys all things. Black holes are more than a thought experiment. They are believed to occur in the universe in at least two situations. One is along the lines of the previous discussion of neutron stars. When large stars run out of nuclear fuel, they collapse in on themselves. This collapse is a messy process in which a great deal of matter is blown off into the surrounding universe in an explosion called a supernova. In fact, it's generally thought that supernovae play a crucial role in distributing metals and other moderately heavy elements throughout the universe. Enough mass can remain behind that it is impossible for a neutron star to form and also remain stable. Instead, this remaining mass collapses to form a black hole, whose mass is at least a few times the mass of the Sun. The black holes whose mergers were observed by LIGO are somewhat more massive, but still plausibly produced by stellar collapse. Much larger black holes are thought to exist at the center of galaxies. Exactly how these black holes formed is more mysterious and may be related to dark matter, the physics of the very early universe, or both. Black holes at the center of galaxies are tremendously massive, containing thousands to billions times as much mass as the Sun. One is thought to be at the center of the Milky Way, containing some 4 million solar masses. We may well ask, how can we be sure that a black hole is present if no signal can escape from a black hole horizon? The answer is that nearby objects respond to the gravitational pull of the black hole. By tracking the motion of stars near the center of the Milky Way, we can be certain that a very massive, very dense object is present there. We cannot prove in this way that it is a black hole. What we can say is that if it isn't a black hole, then it's something much stranger. In short, black holes are the simplest possibility, and the modern consensus is that they do exist at the centers of many, if not most, galaxies. Black holes are a tremendously useful theoretical laboratory because they are mathematically simple compared to most astrophysical objects. Stars are really very complicated. Nuclear reactions at the core of stars provide their power. The matter inside stars experiences pressures and fluid dynamical motions that we can simulate numerically, but certainly do not understand completely. And stars have surface dynamics which are probably as complicated as the Earth's weather patterns. A black hole, by comparison, is wonderfully simple. In the absence of other matter, black holes must settle down to one of a few definite forms, all of which are explicitly understood as curved geometries which solve Einstein's equations of general relativity. To be sure, infalling matter complicates the picture, but there is a tolerably good understanding of how ordinary matter behaves as it falls into black holes. Nowadays, there is even a good numerical understanding of what happens when one black hole collides with another, and a central aim of Chapter 6 of this book is to explain how this understanding is achieved and what it means for experiments such as LIGO. Where things get strange is that black holes aren't really black. Using quantum mechanics, Stephen Hawking showed that black holes have a definite temperature related to their surface gravity. In fact, there is a whole field of study known as black hole thermodynamics, in which geometrical properties of black hole solutions are put into precise correspondence with properties familiar from the study of heat, temperature, energy, and entropy. There is even a proposal that black holes in distant parts of the universe may have overlapping interiors, and that these overlapping interiors help encode a quantum effect known as entanglement. We will give an introduction to these subjects in Chapter 7. Black holes continue to grip the imagination of scientists to this day. Astronomers search for ever more precise evidence of the properties of spinning black holes, and now they eagerly anticipate collaboration with gravitational wave observatories to understand the cataclysmic events surrounding black hole mergers. And this is just the beginning for gravitational wave astronomy. With a worldwide effort underway to build a network of detectors in the United States, the 2 LIGO detectors in Hanford, Washington, and Livingston, Louisiana, Europe, Virgo and Geo 600, Japan, Kagra, and India, LIGO, India. Meanwhile, string theorists study black holes in higher dimensions, not only as a means of probing quantum effects in gravity, but also as analogues of physics as diverse as heavy ion collisions, viscous fluids, and superconductors. And black holes inspire us all to ponder the strangest questions. Could black holes ever be useful to us? What really lies inside them? What would it be like to fall into one? Or is it possible we've already fallen in and just don't know it yet? Chapter 1. Special Relativity. To understand black holes, we have to learn some relativity. The theory of relativity is split into two parts, special and general. Albert Einstein came up with the special theory of relativity in 1905. It deals with objects moving relative to one another, and with the way an observer's experience of space and time depends on how she is moving. The central ideas of special relativity can be formulated in geometrical terms using a beautiful concept called Minkowski spacetime. General relativity subsumes special relativity and also includes gravity. General relativity is the theory we need in order to really understand black holes. Einstein developed general relativity over a period of years, culminating in a paper in late 1915, in which he presented the so-called Einstein field equations. These equations describe how gravity distorts Minkowski spacetime into a curved spacetime geometry. For example, the Schwarzschild black hole geometry that we will describe in Chapter 3. Special relativity is simpler and easier than general relativity because gravity is neglected. That is, gravity is ignored or presumed to be too weak an effect to be significant. Special relativity includes the formula E equals mc squared, relating energy, E, mass, m, and the speed of light, c. This is one of the most famous equations in all of physics, possibly in all of human understanding. E equals mc squared made it possible to foresee the awesome power of nuclear weapons, and it is at the core of our hopes, as yet unrealized, for a clean source of energy from nuclear fusion. E equals mc squared is also very relevant to black hole physics. For example, the 3 solar masses worth of energy ejected from the first observed black hole collision is a prime illustration of the equivalence of mass and energy. To get an idea of just how cataclysmic this collision was, consider that the mass converted into energy in the explosion of a nuclear weapon, assuming a yield of 400 kilotons, is a mere 19 grams. Special relativity is closely related to James Clerk Maxwell's theory of electromagnetism. Indeed, an early hint of the relativistic view of space and time emerged in the late 1800s in the form of so-called Lorentz transformations, which explain how observers' perceptions of electromagnetic phenomena depend on how the observers are moving. The most familiar electromagnetic phenomenon is light, which is a traveling wave of electric and magnetic fields. A consequence of Maxwell's theory is that light has a definite speed. Relativity is built around the idea that this speed is truly a constant, independent of the motion of the observer. The motion of observers is described in special relativity in terms of frames of reference. To get an idea of what a frame of reference is, think of a high-speed train. If all the passengers are seated and all the luggage is stowed, then everything on the train indeed is stationary with respect to the train itself. But the train is moving quickly relative to the Earth. Let's assume that the train is moving in a straight line at constant speed. To give a fully precise account of frames of reference, we should stipulate the absence of any significant gravitational field. For example, instead of a train running at constant speed along the Earth's surface, we would need to consider a spaceship coasting at constant speed in otherwise empty space. Earth's gravitational field is weak enough that, for present purposes, we can ignore its effects on the train and work with just the special theory of relativity rather than the general theory. Without looking out the windows, it's hard to tell how fast the train is moving. In a situation where the train has fantastic suspension and the track is very even, and where the blinds on all the windows are down, it would be impossible to know that the train is moving at all. The train provides a frame of reference, the one that its passengers naturally use to judge whether something inside the train is moving. They can't tell, in the ideal situation just described, whether the entire train is moving, but they certainly know when someone walks up the aisle, because such a person is moving relative to their frame of reference. Furthermore, all physical phenomena, like balls dropping or tops spinning, would behave the same, as observed by an observer on the train, whether the train is actually moving or not. Briefly then, a frame of reference is a way of looking at space and time which is associated with an observer or a group of observers in a state of uniform motion. Uniform motion means that the train is not speeding up or slowing down or turning. If the train is doing one of these things, then the passengers will notice. For example, rapid acceleration pushes them back in their seats, whereas rapid deceleration throws them forward. Let's imagine our train passing through a station without stopping or slowing down. The passengers on the train, call them Alice, Alan, and Avery, are observers in a moving frame of reference, which we'll call the A frame. Meanwhile, their friends Bob, Betsy, and Bill stand on the platform in a stationary frame of reference, which we'll call the B frame. To draw these frames of reference, we put B frame position on the horizontal axis and B frame time on the vertical axis, and we map out the trajectories of our various observers through space and time, so that over time, B-frame observers always stay at the same B-frame positions, whereas A-frame observers move forward. The resulting diagram is actually Minkowski spacetime. The word spacetime refers to the fact that we are showing space and time on the same diagram. It's possible to take a different perspective on Minkowski spacetime, such that A-frame observers are shown as stationary, while B-frame observers move backward. More on that perspective later. Special relativity hinges on the assumption that the speed of light is constant. In other words, the speed of light is supposed to be the same when measured by the observers on the train as when measured by the observers on the platform. If that weren't so, then by measuring the speed of light, an observer could tell which of the two frames of reference she was in. But a core tenet in relativity theory is that physics should be the same in any frame of reference, so that you really can't tell which frame you're in through any physical measurement. According to this tenet, we cannot pick out a frame and say, remaining in this frame is what it means to be stationary. Motion consists of being in a different frame. We can only say, any frame is as good as any other. The only idea of motion that we can permit is motion of one observer with respect to another. In other words, states of motion are not absolute. They are relative. Thus, it was a misnomer to refer to the A frame as moving and the B frame as stationary. All we can really say is that they are moving with respect to one another. The idea of the B frame being stationary seemed natural, though, because we were implicitly thinking of motion relative to the Earth. The intuition we've explained about relative motion seems like common sense, and we should ask ourselves how we can possibly get any leverage from it on questions relating to the deep nature of space and time. The key ingredient is Maxwell's theory of electromagnetism. What this theory tells us, among other things, is that if Alice pulls out a laser pointer and sends a pulse of light forward toward the front of the train, and Bob does the same, then the two light pulses travel forward at exactly the same velocity. This seems like another innocuous claim, but it's not. For example, if we arranged for the train to go at 99% of the speed of light, so obviously not an American train, then wouldn't Bob measure a laser pulse shot forward by Alice to be traveling at almost double the speed of light? After all, she is moving forward at 99% of the speed of light relative to Bob, and her light pulse moves forward at the speed of light relative to her, so it seems like Bob should measure her light pulse to be moving forward at 199% of the speed of light. But according to electromagnetism, he doesn't. He measures it to be moving at precisely the same speed of light relative to him that Alice would report if she measured its motion relative to her. How is this possible? The answer is that Alice and Bob measure the passage of time differently, and they also measure length differently. The details of how this happens are encoded in the Lorentz transformation, which is a mathematical expression relating time and length in the A frame to time and length in the B frame. A Lorentz transformation is easy to draw using Minkowski spacetime. Before the Lorentz transformation, we can think of the B frame as stationary and the A frame as moving forward. After the Lorentz transformation, the A frame is stationary and the B frame is moving backward. A Lorentz transformation is just the change of perspective between the account that Bob would offer based on thinking of his frame as stationary and the one that Alice would offer based on thinking of her frame as stationary. Key consequences of the Lorentz transformation include time dilation and length contraction. We're going to explain time dilation first because it's easier to describe. Suppose that at noon on Friday, you get on a train at Princeton Junction. For convenience, we're going to say that this time and place correspond to the origin of Minkowski space, where the t and x axes cross. Now, there are fast trains and slow trains that go through Princeton Junction. Some go north toward New York, and some go south toward Philadelphia, and you can decide which one you want. What you're going to do is ride the train for exactly 1 hour by your watch, and then get off and mark where you end up. Obviously, if you take a fast train, you'll get farther. But beware of the assumption that you get exactly twice as far riding a train that goes twice as fast. The tricky part is that you're riding the train for exactly 1 hour as measured by your own watch. The speed of a train is something observers who are stationary relative to the ground would measure, and their watches run a bit differently from yours because they're in a different frame of reference. So where do you end up? More generally, if you and a bunch of friends all take different trains, all departing Princeton Junction at the same time, where do you all wind up? The answer is that you all wind up somewhere on a hyperbola in Minkowski spacetime. In other words, the hyperbola is the set of all possible final locations that you can reach after precisely 1 hour of your own travel time. One possible final location is Princeton Junction itself at precisely 1 p.m. Princeton Junction time. The way you wind up there after an hour is if you are silly enough to spend an hour on a train that doesn't move at all. In that situation, of course, it's 1 p.m. Princeton Junction time when you arrive, because your frame of reference is the same as the station's, so that your watch exactly keeps pace with station time. If instead you get on a train that actually goes somewhere, your watch runs slower than station time. So when you get off after an hour of perceived travel time, station time is actually later than you think it ought to be. This later than you think effect, known as time dilation, is captured in Minkowski spacetime by the way the hyperbola curves upward in the time direction as you go to locations farther and farther from your starting point. Minkowski spacetime is sometimes called hyperbolic geometry, in reference to precisely the type of hyperbola we have been discussing. In Minkowski spacetime, we visualize the constant speed of light by drawing light rays at precisely a 45-degree angle relative to the vertical time axis. You'll notice that the hyperbola of possible endpoints for a 1-hour train ride is wholly within the region of spacetime between two light rays emanating from the origin. This is the way Minkowski spacetime encodes the statement that none of our trains can go faster than light. It may seem like our discussion of time dilation doesn't have much to do with Lorentz transformations. To see that it really does, let's go back to calling the reference frame of the train the A frame, while the reference frame of the Earth is the B frame. Suppose Alice spends an hour in the A frame on her way from Princeton Junction to New York. Meanwhile, Bob and his friends remain stationary with respect to the Earth. How should they figure out the time of Alice's arrival? It's not very useful for her to call them when she arrives, because the signal she would use could only travel at the speed of light, and Bob and friends would have to do a calculation based on the time they received her call, the speed of the signal, and the distance to New York City to figure out when Alice arrived. That all sounds too tricky. So Bob figures out a better way. He synchronizes his watch with one of his friends. let's say Bill, and Bob and Bill take up positions at the Princeton Junction and New York City train stations, respectively. Bob measures when Alice leaves.
Sample complete. Ready to continue?